In part 5 of this series, we're asked to find the force of pressure for the following object. It is a quarter of a circle, and the question reads, the area below is submerged in water, where the density of water is shown right here, so that the origin is 10.0 meters below the surface. Find the force on the area. In every question that we did from part 1 to part 4, we used this formula. And it ended up giving us the amount of force in newtons that's exerted on an object that has been placed in water, kind of like a dam. This time, however, they're asking us for the force of pressure. And notice the difference in the formulas. Here we multiply the density, which I'm representing this time by a different Greek letter, delta, times y bar, which represents the y coordinate of the centroid, times the area. This is very similar to the formula that we used before. Aside from the fact that we used rho to represent density before, this part represented the depth as a function of y, whereas w at y dy represented the width of the shape as a function with respect to y. So by multiplying these two, this part to this part, we found the area. Now this has been replaced in our new function. We have our area, which we'll find right now. We'll multiply it by the y coordinate of the centroid, and altogether this should give us force of pressure. So let's go ahead and answer this question. What we first have to do is find the area of this object. And remember the different approach we used in parts 1 through 4. We took tiny rectangles all throughout the object as a function of width and height. This time, to find the area, we'll just integrate the function itself. As mentioned, this is a quarter circle, and this right here, x is equal to 1. To find the area of this thing is not hard to do. We say area is equal to the integral between 0 and 1, and our function, we have to make it into y is equal to. We currently have y squared, so I square root both sides, and I end up with plus minus 2 times the square root of x. I'm only going to use the positive version because it is above in the first quadrant. And I'll replace that right here, dx. I'll integrate this part, pull out that 2, integrate the square root of x, which is equal to x to the power of half. Integrating this, or the antiderivative of this, would be 2x to the power of 3 over 2 over 3. And now I'll find out what this is when x is 1 and when x is 0. When x is 1, this is 2 over 3. When x is 0, this is 0. So I'm going to multiply 2 over 3 times 2, and I end up with 4 over 3 meters squared. This is the area. Remember, our formula is force is equal to the density, which is represented by the Greek letter delta, times the y coordinate of the centroid, times their area, which is 4 over 3. I'm also going to replace this now with 1,000. 1,000 times the y coordinate, 4 over 3. Now, to account for the fact that it is beneath the surface of water, we know that the y coordinate of the centroid is 3 over 4. But since it's submerged, what we have to do is take the distance at which it is submerged and subtract it by the y coordinate. So I'll take 10 minus 3 over 4. So this part, I'll replace it with this. Now I'll multiply 1,000 times 4 over 3 times 10 minus 0.75, which is what a quarter is equal to. That gives us 12,300. 12,300 kilograms. Reason why is because the units of this is in kg per meters cubed. This one is in meters squared, and this one is in meters. So this cancels out with these three, leaving us with just kilograms. Or you can convert this to tons, which is 12.3 tons. And there you have it. That is how to express fluid pressure force as an integral.